Good day, grade 10 learners. Welcome to our second quarter lesson in science, specifically on physics. Today, we will discuss the discovery and nature of electromagnetic spectrum. At the end of this video, you should be able to track how electromagnetic wave was discovered through electromagnetic induction, describe the characteristics of electromagnetic waves, identify the regions of electromagnetic spectrum, and determine the ranges of wavelengths and frequencies each region. Let us now begin our journey in the discovery of electromagnetic spectrum. It all started in Hans Christian Ørsted. Born on 1777 and died on 1851, Hans Christian Ørsted is a Danish physicist and chemist and a professor in the University of Copenhagen. In 1819, he discovered during a class demonstration that a current-carrying wire would deflect the compass needle. He inferred that an electric current would induce a magnetic field. Next to Ørsted is the discovery of electromagnetic induction by Michael Faraday. In 1831, he found that upon passing a current through one coil, a momentary current was induced in the other coil, a mutual induction. If he moved a magnet through a loop of wire, an electric current flowed in that wire. Further conceptual developments of electromagnetic induction led to electromagnetism. André-Marie Ampère discovered that a current-carrying wire can attract or repel another current-carrying wire next to it. He formulated the Ampere's law of electromagnetism. We now have James Clerk Maxwell, wherein in 1865, he discovered that a changing magnetic field will induce a changing electric field, leading to the existence of electromagnetic wave. And lastly, Heinrich Hertz discovered the existence of radio waves, and he was the first person to transmit and receive controlled radio waves. These concepts on electromagnetism led Maxwell to propose electromagnetic wave theory. It states that light is an electromagnetic wave that is a transverse wave that is partly magnetic and partly electrical in nature. The magnetic wave and the electric wave are perpendicular to each other, as was shown in this figure. Now, describing the characteristics of electromagnetic waves, it is a type of mechanical wave that the direction of the wave is perpendicular to the motion of the wave. It can travel with or without medium, and it travels in 3 times 10 raised to the power of 8 meters per second, or it travels in the speed of light. We have now unfolded the nature of electromagnetic waves. Let's move forward to the electromagnetic spectrum. The electromagnetic spectrum is composed of gamma ray, X-ray, ultraviolet, visible, infrared, microwave, and radio wave. From long-wave red to short-wave violet, let's now determine the characteristics of each region of the electromagnetic spectrum in terms of wavelength and frequency. Radio wave has the longest wavelength, measuring 1 millimeter up to 100 kilometers among the electromagnetic spectrum. It also has the least energy and frequency, having 3 kHz to 300 GHz. Microwave has the shorter wavelength than the radio wave. It measures from 30 centimeters to 1 millimeter. The frequency is greater than the radio wave but less than the infrared, measuring 3 times 10 raised to the power of 9 up to 3 times 10 raised to the power of 11 hertz. Infrared has the shorter wavelength than the microwave, measuring 780 nanometers up to 1 millimeter. The frequency is greater than the microwave but less than the visible light, 10 raised to the power of 11 up to 4 times 10 raised to the power of 14 hertz. Visible light extends from shortwave violet to longwave red. Its wavelength is shorter than the infrared, measuring 740 nanometers up to 380 nanometers. Its frequency is less than the violet, measuring 4 times 10 raised to the power of 14 up to 7.5 times 10 raised to the power of 14 hertz. The table shows the variations of wavelength, frequency, and energy of each colors of visible light from red up to the violet. Red has the longest wavelength, having 760 nanometers, while violet only measures 410. In terms of frequency, red has 4.62 times 10 raised to the power of 14 hertz, while the violet has the highest frequency of 7.50 times 10 raised to 14 hertz. When it comes to energy, red has the least energy, measuring 1.91 electron volts, while violet has 3.10 electron volts. Ultraviolet has the shorter wavelength than visible light, measuring 1 times 10 raised to negative 8 to 4 times 10 raised to negative 7 meters. The frequency is greater than the visible light but less than the gamma ray, measuring 7.5 times 10 raised to 14 to 3 times 10 raised to 15 hertz. X-ray has the shorter wavelength than ultraviolet, measuring 1 times 10 raised to negative 11 to 1 times 10 raised to negative 8 meters. The frequency is greater than the ultraviolet but less than the gamma ray, measuring 3 times 10 raised to 16 to 3 times 10 raised to 19 hertz. Gamma ray has the shortest wavelength among the entire electromagnetic spectrum, measuring its wavelength less than 1 times 10 raised to negative 12 meters. It has the highest frequency among the electromagnetic spectrum, measuring 3 times 10 raised to 19 to 3 times 10 raised to 26 hertz. So these are the description of each electromagnetic spectrum in terms of frequency and wavelength. With the highest frequency among the electromagnetic spectrum, gamma ray possesses the highest energy, while the radio wave at the other end possesses the least. Let me end with this saying: when the first "let there be the light" spoken, the entire electromagnetic spectrum is emitted by Toba Beta. Thank you for watching. Stay tuned in our next video covering the different applications of electromagnetic spectrum. For more video lessons, follow the Facebook page and YouTube channel of Exploring Physics. Bye!